Hello everyone. Now we want to practice linearization of the equation that we got from the deriving of the heat and mass balance on this system, which was a continuous simultaneous heating and liquid level changes in the tank that we have both heater and pump in the system. In order to do linearization of a nonlinear, actually ODE, we can use the first order Taylor expansion, and we expand it around the steady state point. Now I assume that this dt to dt, which is the ODE equation, equal to function of four variables. The first one is omega I, which is the inlet mass transfer. The second one is the heat energy or energy of the heater which comes to the system. The second one is the temperature of liquid inside the tank or outlet of the tank, and elevation of or height of the liquid inside the tank. Knowing that, and also considering the Taylor expansion, we can write dt is almost equal to if at a steady state, so all variables at a steady state we will show with bar. Omega I q bar means q at a steady state, t bar t at a steady state, and elevation at a steady state, plus the first derivative of function around the based on omega I at a steady state point, multiplied by omega I minus omega I at a steady state, which we show by bar. The first derivative of f based on second variable, which is q, and there is the second input to the system, and we multiply q by q minus q bar, plus the first derivative of f based on temperature, the first state of the system, and we multiply it by t minus t at a steady state, plus the first derivative of f based on the last variable, which is elevation, and we define it at a steady state. Also we multiply it by h minus h at a steady state. Now is a matter of just substituting all these derivatives by the value that we have. Okay, so let's go back to the function and see what would be the first derivative of f based on wi. I will write it like the first actually let me change the pen color to green, then we can see better. So df by d omega I at a steady state is equal to omega I has cti and ct as multiplication. So we will write first the constant parameter which are outside the parentheses, rho a c, and then we take the derivative of inside the parentheses, so it would be c ti, or I can bring c because c is also constant outside the parentheses, and then inside the parentheses I will have only ti bar and t bar divided by h bar. The second, actually c can cancel by this c. The second derivative is changes of f based on q equal to 1 divided by rho AC multiplied by 1 divided by h at a steady state. Also, the first derivative of f by h equal to, or t actually, the second one is t, the third one is t, and we define it at a steady state, is equal to 1 divided by rho a multiplied by omega I bar divided by h bar and then we will have ln f by ln h defined at steady state equal to 1 divided by rho AC minus omega I CTI minus omega I CT plus Q divided by h bar power 2. Also we know that f is defined at a steady state f at a steady state is equal to omega I bar q bar t bar and h bar would be 1 divided by rho a c multiplied by omega I bar c t I bar minus omega I bar c t bar plus q bar divided by h bar. Also we know that f at a steady state is equal to 0 because actually we don't have any changes of temperature based on time. So when the left hand side of the equation is equal to 0, the right hand is also equal to 0. So we will see that this is equal to 0. Also, if we look at the first derivative of f based on h, we will see it has the same, actually we have to define it at a steady state, so we need to put the bar sign on top of it, so omega I bar, ti bar, omega bar, t bar, q bar and h bar. So it's identical to the value of f at a steady state, except that we have power 2 on the edge, so this is also equal to 0. I can say this is also equal to 0 and then we can eliminate it from the equation. We don't have any changes of f based on elevation, as we can see. So the only thing is that we define some deviation variables which makes us actually make the system more easier. Actually here if we say omega I minus omega bar is equal to omega tilde, and then we can define q minus q bar as q tilde, and also t minus t tilde t bar equal to t tilde. Same for h. Elevation minus elevation at the steady state, we define it at h tilde. And then we can write the equation in a more simplified version, which is nothing but this one. dt tilde by dt can be written as the linear form of and simplified format of the first derivative of f based on omega tilde, actually omega tilde 1 I, plus the first derivative of f based on q at a steady state multiplied by q tilde, the first derivative of f based on elevation, we don't have this, so we put 0, the first derivative of f based on temperature, and we define it at a steady state and we multiply it by t tilde. Now we actually, the only thing is that we substitute all these parameters by the differential variable values that we have. The next step would be using the Laplace transform in order to get the transfer function. That we will explain it in our next lecture. Thank you.